Professor Wada.
Thank you.
Although I did not understand what you said, I trust that it was good things. So there we go. And let me hide the floating controls. So I think that should be good. Thank you for the introduction and greetings to everyone from the University of Illinois at Urbana-Champaign in the USA. I deeply regret that I'm not able to be with you in Tokyo today and to deliver this lecture in person. It's been over 3 years since I last traveled to Japan, and I really miss all of you, my colleagues and my friends. And I sincerely hope that this pandemic ends soon and that we can once again enjoy together. Nonetheless, I'm happy to share with you today some of our recent work on topology optimization of structures subjected to stochastic excitation. In preparation for this lecture, I had a chance to reflect on how fortunate I am to have so many friends and colleagues in Japan. Indeed, it's been nearly 30 years since I first met Professor Iyamura in Palm Springs, California in 1993. Later that year, I met Professor Akira Nishitani and Professor Fujino in Honolulu. And then in 1995, I had the opportunity to visit Japan for my first time. And I traveled throughout Japan on that occasion, but in particular, I gave a lecture at the third colloquium of vibration control of structures by the Japanese Society of Civil Engineers. I then, in 1996, met Professor Seto from Nihon University in Seattle, Washington, and then Professor Kawashima in San Francisco, and then Professor Wada. And I believe that there was a huge snowstorm in Chicago, and we had the occasion to spend some time together going to Purdue University. And then Professor Tamura in 2002 at the University of Notre Dame when he was visiting Hassan Karim. And so many other people that have been kind to me and been collaborators and that I have enjoyed meeting. As a result of those collaborations, there's been numerous students and researchers that have visited my laboratory, and including the last two. Let's see if I can get a pointer. Narazaki, he is at Yasutaka Narazaki. He's now an assistant professor at the joint ZJU-UIUC campus, and Koji Tsuchimoto, who works for Taisei Corporation. But this has just been such a wonderful part of my life. And I'm grateful to all of them. But on to the technical presentation. First, I'll give you a brief introduction to topology optimization and why we are interested in stochastically excited structures. I'm then going to move on to the problem formulation and numerical implementation. And then I'll discuss applications and provide some concluding remarks. So first, let me move over to the introduction. There are three main approaches to structural optimization. The first is what we call size optimization. That's where we already have the structural members, location, connectivity, and what we do is we just adjust the size of these members. There's also what we call shape optimization, where we basically have the form of the structure, but we can adjust the particular shapes. But for example, in this case, we cannot add an additional hole or remove a hole from this structure. And then there's topology optimization. This was the first paper on this topic was by a Japanese professor who's at the University of Michigan and another professor in Denmark, 1998. And their idea was that we should be able to choose the location and connectivity of the material so that it best fits the needs of our structure. Now, probably one of the most famous examples of topology optimization was for this Airbus A380, where they saved about 500 kilograms on the leading edge. But there's also a number of structures that have been in the civil engineering arena that have used topology optimization, including the Stuttgart Airport, more of a grounded structures approach, the Qatar National Convention Center. And on the top right is some work of Bill Baker and Glaucio Paulino. Glaucio Paulino is now at Georgia Tech, but he used to be at the University of Illinois. And for those of you that have interest, I might point you to this website. If you could, you may want to quickly write that down. There are a number of free programs where you can try topology optimization. There's a 99-line MATLAB code. And then there's a number of apps that you can put on your phone where you can apply the loads, you can select the domain, and then you can see what the optimal topology is. However, despite nearly 35 years of research, the majority of topology optimization applications only deal with static loads or simple deterministic dynamic loads. Topology optimization of structures subjected to stochastic dynamic loads has been very limited. Yet most of the loads that civil engineering structures experience are stochastic in nature. For example, earthquake loads, wind loads, wave loads, and traffic loads. And so if we want to develop optimal topologies, optimal forms for civil engineering structures, we need to take the stochastic dynamic nature of the loads into account. So let me go through the problem formulation, how we deal with this particular situation. First is the modeling of the excitation. And we're going to model our excitation as either a stationary or non-stationary filtered white noise. In this example, you can see the Kanai-Tajimi model, where we have a white noise goes into an excitation model or a filter, and then the output is the stochastic excitation, which maybe we'll also put an envelope to give the non-stationary nature of the excitation. Well, this can be generalized to not just a simple second order filter, but more complicated filters, vectored white noise inputs, so that we can even create random fields to represent the loads on our structures. In the case of the Kanai-Tajimi spectrum, that filter in the red box would have the matrices associated with what I've written down here at the bottom. And there's a book by Sung and Gregorio, written in 1993, which gives a good overview of these types of stochastic models. So what we want to do then is we take that excitation model, we input it into our structural model to obtain the stochastic structural responses. And these two boxes in the middle, the red and the purple box, we combine together to create an augmented system. And because we have a white noise input, then we have the responses characterized by the covariance matrix, which satisfies the Lyapunov equation or the non-stationary Lyapunov equation. You might note that the stationary responses are algebraic equations, that is of the form, they're static equations, F equal Kx type of equations. And the non-stationary response is governed by a simple vectored linear ordinary differential equation. Once I have gamma, then I can calculate the responses of any of the locations or the types of responses on my structure. And again, Soong and Gregorio talks about this type of procedure. Now, what we do is we combine that with the topology optimization framework, where our goal is to find the element densities. So in this diagram over here on the right, let's see. This diagram over here on the right, we're going to select the density of the elements. As you can see, if it is white, that's the minimum density, and that would be equivalent to not having the structure there. If it's gray, maybe that corresponds to 50% density. And if it's 1, black, that would correspond to full density. And so our goal is to formulate some sort of an objective function that's in terms of the stochastic structural responses. And we want to make sure that we satisfy the constraints. And this objective function, J of Z, can be in terms of the important things to structural engineers like displacements, interstory drifts, accelerations, or any one of the degrees of freedom, maximum values, even failure probabilities. And we would have that formulation as some functional relationship as shown here. So the covariances will be a function of the density variables Z. In doing it in this way, the stochastic topology optimization problem has thus been converted into an equivalent deterministic optimization problem in terms of the response covariances. What that means is that we don't have to run Monte Carlo simulation. So how do we solve this problem? We initialize the problem. We conduct the analysis using an alternating direction implicit method to solve the Lyapunov equation. We then calculate the sensitivities. And this shows our proposed method, which is a solution of an additional Lyapunov equation. So the machinery that we put together to get the covariances can also solve for the sensitivities. And this just compares the proposed approach to the traditional finite difference methods. We then update using standard method of moving asymptotes methods. And then we ask, is it convergent? If no, we repeat the analysis. If yes, then we're yielded the optimal topology. Now, one thing I just wanted to show you that we've implemented, this is, I won't go into too much in the way of details, but in general, many optimization problems require a minimax objective function. What that means in this case is I want to minimize the maximum interstory drift. And at the point there in the middle here, you can see there's a discontinuity when it goes from one of the interstory drifts governing to the other. Where you have that discontinuity generally causes failure of solution methods that are based on gradients. And so what we do to solve this, there are non-smooth optimization methods, but they're generally inefficient, and for large problems, they fail. And so what we did, we've looked at a couple approaches, but this KS formulation, it uses an approximation, a smooth approximation to the mini-max problem. And this is the equation just for your reference. And there's a parameter in there, rho, which we increase about every 10 iterations until we get convergence. Now, it's easier to understand that in terms of a picture. So the picture on the left is the actual objective function, the minimax objective function. And what we do with this KS formulation is we'll take the objective function and we'll approximate it with the black line. We'll do several iterations to get close, and then we'll increase rho. This is for rho equal 1, this is rho equal 10, and this is rho equal 100. So as we get closer, we can make a more sharp transition until we converge on the optimal solution. So one of the unique features about our work is we're often minimizing the maximum interstory drift, or the maximum of the variables that are of interest. So use of this minimax function, you might think, gee, that's going to increase my computational time tremendously, but it's only about a 7.5% increase in the computational time for the examples considered. Well, that's probably a little bit more theory than what you bargained for. So let me now turn to the applications. And the first application, it's a simple 3-story building to illustrate what we're looking at. The volume constraint, that means 30% of the area can be material. If it were 100%, it would be entirely black. We're using Rayleigh damping and the Kanai-Tajimi spectrum for the excitation. So this shows you, on top is the performance function, the objective function, and on bottom is the constraint. And so as we start iterating, the shape of the structure which best minimizes this interstory drift, it's the sum of the 3 variances of the interstory drifts, the structure very quickly is found. Now, one of the things that we all know is that it's not only the interstory drift or the safety considerations, but it's also the serviceability related to the accelerations. In this particular building, this is the John Hancock Tower in Boston, and I think most of us know that the upper floors experienced severe motion, and with many of the occupants becoming sick. And so they had to retrofit this structure and install 2 300-ton TMDs to get the acceleration and displacement levels to be within reason. So the formulation that we consider can not only accommodate displacement objectives, but you can include an acceleration objective also. So you can have different flavors of your design, considering accelerations and displacements, or some combination of the two. The first structure considers only minimizing the displacements. The second structure has some weight, 0.2 on acceleration, and the third has more on the acceleration. What this allows us to do is to have a Pareto optimal front, where we have all of the feasible designs. The feasible designs are over here. And what we see is that the original structure was at this black point as shown. The structure which minimizes the displacement is on the bottom floor. So it minimizes the displacement, but that results in high acceleration. Accelerations are on the y-axis. And this is the structure with alpha equal 0.2. And what you see is that down here, these are infeasible designs. So anything in this upper region I can achieve, and this Pareto optimal front allows me to make the design trade-offs between minimizing accelerations and minimizing interstory drift. Now let me move on to my second example. This is a benchmark building, a 9-story benchmark building that was designed by the SAC Consortium after the Northridge earthquake. We're again using the Kanai-Tajimi spectrum. We have lumped masses, and there are columns carrying the gravity loads on the left and the right. And what we're looking is to consider the bracing system. So what we have here, I wanted to show you, what if we just minimize the static compliance. That corresponds to this blue line. And what you see is that if we're going to minimize the static compliance, then I have good, the interstory drifts at the lower floors are very good, but at the upper floors, I have quite high interstory drifts. If I'm going to minimize the sum of the variances, which is what's done by many people, and what I showed you in the first example, I get the red curve. And what you see is that we get good performance, better than the static compliance problem, but we still have higher interstory drifts on the upper floors. If I solve the mini-max problem, which I showed you earlier, then I get equal interstory drift on all floors. And so this is the optimal design for the mini-max problem. Now let's look at another problem. This is the, again, it's a benchmark structure, 20-story benchmark structure designed by the SAC Consortium in California after the Northridge earthquake. And what we looked at here was just the above ground floors. We didn't model the 2 basement floors, and we're just modeling one plane of the moment frame. So it's 20-story, 5 bays at 4 meters each for the floors, and then 6 meters per bay. Steel construction, we've got a volume of 20%, and the columns vary linearly. So Rayleigh damping, 2% in the first and second mode. And our goal is to minimize the variance of the maximum drift. I want to point out this particular building and the associated code was developed by Professor Otori, who visited me in the late 1990s at Notre Dame. So we looked at 2 soil configurations. First is the medium soil configuration, and we assumed here a rigid diaphragm in the floors. And you could see a very nice mega brace configuration. And so then we considered, well, what if we had firm soil? And what you see is that the design is by and large the same. So what that says in this case is that the design of this mega brace system is not very heavily related to the assumptions on the input earthquake. Now, this was for the rigid diaphragm assumption. What if we considered a flexible diaphragm? What you see, and I'll switch back here, because of the rigid diaphragm up in the upper floors, we don't need to have much additional bracing. But when we have flexible diaphragms, you can see that additional bracing is required to tie the various column motions at the top together. This is the medium soil, and this is the firm soil. You can see that, again, there are some differences, but by and large, these 2 structures are similar. So what we wanted to do was to consider the case where you excited the structure with the firm soil design by the medium soil excitation. And you see that you don't get perfect equal variances of the interstory drifts, but it's not off too much. And the optimal design, that is when you have a medium soil excitation and you've designed for that, then you get the optimal equal interstory drifts, variances of the interstory drift. Similarly, if we have a firm soil excitation, a higher frequency excitation, if you design for the firm soil, then you get equal interstory drifts. And if you, so what this says, I lost the conclusion. What this says is that our designs are robust to the earthquake parameters. I want to turn now to topology optimization and damper placement as a simultaneous optimization problem. And we found some very non-intuitive results here. So this is the building. We have both intrinsic damping, and we also have discrete dampers that are placed in the building. The discrete dampers are going to be proportional to the velocity, interstory velocity, and will minimize the response of the structure due by placing the material and the dampers at appropriate places in the structure. Let me show you more specifically. This is the design if we just optimized the topology. Now, if we went in after the structure was designed, after the topology was optimized, and we placed the dampers to minimize the interstory drift, these are the location and the size of the dampers which would minimize the interstory drift. That's a little bit surprising. We always think of having the dampers being on the first couple of floors. Now, if we simultaneously optimize the topology and the dampers, you can see that we're going to get different types of topology. Here you can see this bracing has changed down here. The supports in the upper regions have changed, and the distribution of damping has changed. You want one large damper on the ground floor, and then you have some damping at the top to keep those from flapping around. As a matter of fact, if we look at the comparison of the various responses, this simultaneous optimization of topology and damping gives us equal interstory drifts. Now, if you did independent optimization of the topology and the dampers, you still do pretty well, but you're significantly higher, about 10% higher than, maybe 10 to 15% higher than if you did simultaneous optimization. Now, we thought we'd also look at some traditional approaches for installing dampers. This is putting all of the damping on the first floor. And you can see it reduces the first floor displacements, but the upper floor interstory drifts are still large. Here, this is putting dampers on the first and second floor, and we have still similar problems. Or uniform dampers throughout the structure. And you can see the green here, we still have interstory drifts at the upper floors that are large. So the conclusion here is that simultaneous optimization of topology and damper locations and sizes yields non-intuitive solutions that are significantly better than other common approaches. Let me turn now to wind-excited structures. I was very happy to see Professor Tamura in the audience, and I'm intimidated a little bit because of having one of the world experts in wind engineering in the audience today. But some people have done the topology optimization for structures due to wind loads, but they often treat the wind loads as being static. This is the work of Professor Paulino and Mr. Bill Baker from SOM, where they did the discretization of the wind loads into 6 static loads on the structure. Now, if they had discretized the wind load into 7 static loads or 8 static loads, you get a different structure each time. So as you might imagine, you shouldn't have the optimal topology depending upon how you discretize your structure. So what we have done is we've looked into modeling stochastic wind fields. I think I saw also Professor Xinjong Chen from Texas Tech on the meeting today, and he helped us a lot in understanding the stochastic modeling of wind effect of the wind fields. And so what we would do is you have a given power spectral density of the wind field. We then obtain a model by doing curve fitting in the frequency domain of that power spectral density to get n discrete loads on the structure. And then we interpolate those loads at 1 per floor to give us the wind field. And so what I'll show you today, this is a 76-story benchmark building. It was first proposed by Professor Jan Yang in 2004. I'm sad to say that he passed away earlier this year, but he was one of the great people in structural control theory. And it happens to be that he was the student, the first PhD student of Professor Shinozuka, Masanobu Shinozuka. So we're going to look at this 76-story benchmark building, and we're going to consider the along wind excitation, which is the static mean plus the stochastic fluctuation. And this is what you would get if you look at the RMS interstory drift. Interstory drift, what it says is that the interstory drift at the top of the building is larger than the interstory drift at the bottom of the building. That's counterintuitive for most structural engineers. So let's look at what's happening, what's being done there. At the lower floors, you can see, because for a very tall building, the primary deformation is bending. Some shear, but bending may dominate. And so you can see that at the lower floors, the interstory drift, if you just take U2 minus U1, it's going to be almost zero. But at the upper floors, because of rigid body rotation, you're going to get an apparent large deflection, large interstory drift at these upper floors. And so what this means is the apparent large interstory drift at the top of the building is due to rigid body rotations. So we went ahead and we did a topology optimization minimizing this interstory drift, which is just the relative distances that the two nodes have moved. And you can see that we get, actually, it's a quite attractive topology, and the interstory drift as measured here is reduced substantially. But there's been some work by a number of researchers. This is the paper where we first saw it at the World Conference on Earthquake Engineering in 2012, where they talked about the total interstory drift being comprised of rigid body rotation plus shear deformation. And what they did is they took that rigid body rotation from the I-1 floor, from the lower floor, and then they projected what was called the harmless interstory drift. And then they subtracted that out from the total interstory drift to get what's called the harmful interstory drift, due primarily to the shear deformation. And so if we look at, if we look at the total interstory drift in this structure, in this design, the blue line, then you can see seems quite good. But if you look at the harmful interstory drift, we end up with large lower floor harmful interstory drifts and very small harmful interstory drifts on the upper floors, which that's intuitively what we might expect. But the question is, what if we wanted to minimize the harmful interstory drift in our optimization? So in this example, we're going to look at the along wind excitation, and we're going to look at three design objectives. One is minimizing the roof displacement. Oftentimes in structural engineering design, this will be done. Another is minimizing the maximum harmful interstory drift. And then a combination, because there's good things that come out of minimizing the roof displacement. And so we're looking at a combination of these two objectives. Let me show you what we found. So here are the three designs on the left. There's the design which minimizes the maximum roof displacement. And what you see is that the harmful interstory drift, this is the harmful interstory drift in this plot. It's quite large throughout the structure. And so we wanted to look at another design, which is to minimize the maximum harmful interstory drift. And what you see is we get very good results. But we thought, well, what if we did a combination of minimizing the maximum interstory drift plus some fraction of the roof displacement? And what you see, at least here, is that we get a much cleaner bracing design than if we just minimize the maximum interstory drift. But there's other measures we have to consider. If you look here, this is just the total floor displacement. And if we minimize the maximum roof displacement, we get the blue line. So you can see it gives the smallest result. If we minimize the maximum interstory drift, there's huge roof displacements. And that's not going to be acceptable. But the combination of minimizing the linear combination of the roof drift plus the harmful interstory drift gives us very good floor displacements or roof top displacements. Plus, we get exceptionally good floor accelerations. And so if we minimize the roof displacement, we get large accelerations at the bottom, smaller accelerations at the top. If we minimize the maximum harmful interstory drift, we get larger accelerations, not too bad. But the take-home message is if we use the combined objective function, then we get the best of all worlds. So this gives us, it limits the harmful interstory drift while yielding both small roof displacements and floor accelerations. Now, what is going on there? This is just showing you the modal participation factors for the roof displacement. It's almost entirely a first mode response, whereas the harmful interstory drift has numerous modes that contribute to the response. And so as a result, we can use this trade-off to shape the behavior of the structure. Let me just show you one last quick example. This is just to look at the crosswind excitation, a comparison. We've got three design objectives. Again, roof displacement, maximum harmful interstory drift. You can see it's a little bit complicated. And then when we use the combined objective function, we get very nice results. So with that, I'd like to make a few concluding remarks. First, I hope to have shown you today that we have a general optimization framework to obtain topologies of structures subjected to stochastic dynamic loading. I showed you the solution of the large-scale Lyapunov equations by the alternating direction implicit method, efficient calculation of sensitivities by an adjoint method, implemented a minimax formulation, looked at several numerical examples demonstrating the methodology. And so including this stochastic dynamic wind and earthquake loading directly yields new designs with improved response over approaches employing equivalent static loads. In the future, we're going to look at take and extend the damping optimization to include nonlinear dampers, such are very popular today. We're also going to extend this work to 3D topology optimization. And we're going to look at robust topology optimization so that we can account for uncertainties in the building parameters as well as in the excitation. My two collaborators on this work, they were both my PhD students. The first is Fernando Gomez. He's now an assistant professor in Ecuador at the best university there. He graduated about a year and a half ago. And Juan Carrion, he graduated with his PhD in 2007. He's a professor in Ecuador, but he's also a full-time engineer at Skidmore, Owens and Merrill, SOM, working remotely in Ecuador. If you're interested, these are the papers that I've spoken about today. You can download them from the web, or if you would like, I could send them to Professor Wada and he could distribute them. So with that, I hope that my Japanese here, domo arigatou gozaimasu. Thank you very much for listening today, and I'm sorry for running a little bit over.